Hello everyone. So this is the lecture capture for Lecture 1 for Chem 1001, our chemistry course. And so what we want to do with a lecture capture is give ourselves an opportunity to go back and revisit material that maybe we don't understand or material we missed during the lecture, and this is a great way of doing that. So we're going to start in on Chapter 2 with atoms, and the first thing that we wanted to ask ourselves is what is matter? Well, we can put it in a simple word. We can say that matter is stuff. And a little bit more specific, we can say that it's stuff that has mass and takes up space. Now that's not a really great definition, so we're going to get into this just a little bit more detail as we start to talk about atoms. Now, most matter that we have is fairly easily identifiable. For example, the chair that you're sitting on, the clothes you're wearing, or whatever you happen to be holding in your hand. Some matter, however, is not particularly easily detected. A great example of that is air. It was a very long time before people realized that air had mass, and all gases, for that matter, sometimes they would have reactions that lost a gas, and they would show that matter was not conserved because it appeared that matter actually went down during a gas evolution reaction. People didn't realize that the gas was leaving into the atmosphere, and therefore the reaction itself was losing mass. So it kind of brings us to this point, is during any kind of physical or chemical change, the total mass of all of the matter that went into a reaction can't change. So however much mass went in, that's how much mass has to come out. Now, as we talk about atoms, we're actually going to get below the level of atoms, and we're going to get into subatomic particles. Now, for our subatomic particles, we often express their masses in terms of atomic mass units, or just AMUs. And how much does an AMU weigh? Well, we had to create a relative measure for that. So we base the mass of the AMU on the mass of a carbon isotope, carbon-12. So 1 AMU is exactly 1/12 of the mass of a carbon-12 atom. Our particles sometimes have charges. We see that our proton has a charge there, our electron has a charge there. So here we have our proton with a little positive charge on it, and our electron with a negative charge on it, and our neutron with no charge. And here we see the nucleus containing both our protons and neutrons there. So as far as charges, the charge of an electron is a -1. Charge of a proton is a +1, and these are relative charges. So we can look at their actual charges in terms of coulombs. We see that our proton is indeed positively charged, and it has a very small charge in coulombs, but it is something we're able to measure fairly accurately. We have our electron there that also has the exact same magnitude of charge as the proton, but it has an opposite sign. And so most often we're looking at charges in terms of the relative charge. So we would say a proton is +1 and an electron is -1. And then the neutron, of course, has a charge of 0. We do have kind of our own language in terms of atoms. We have lots of ways of expressing what isotopes we're looking at, or which atom we're looking at. If we look at a chemical symbol here, the full chemical symbol with all three of these numbers on there, A, Z, and X. So X would be the chemical symbol, so something like our Be for beryllium might fit in there. Our atomic number here is the number of protons. I'm just going to call those numbers of P's. So that's the number of protons, and you can take that directly from the periodic table. And then we have this thing over here called mass number, which we have as an A there. And that is actually the number of protons plus the number of neutrons. And that is not something that you can get directly from the periodic table. You need to know what isotope you're dealing with. And we can see that in that chart down below. If we look at something like our neon 20 there, So neon 20, when we look at neon on the periodic table right here, we see it has an atomic number of 10, so that means it has 10 protons. Because we have neon 20, and that is our mass number there, that means that we have 20 total protons and neutrons. So if I have 10 protons and 20 total particles in the nucleus, the remainder must be neutrons. So I must have 10 neutrons to get 20. We see then that for neon 21, we would have 11 neutrons, and for neon 22, we're going to have 12 neutrons. So we can't get the number of neutrons from the periodic table. We do need to know a little bit about what isotope we're dealing with. Now, if we look at those masses of those neon isotopes there, we saw that they all had a different mass. And yet, when we look at the periodic table, we see that there's only one mass listed. So how do we report a single mass of an element when all of the isotopes of the elements have different masses? So what we need to do is find a way of averaging all of those different masses. Now, we don't just use a straight average. We use something that's called a weighted average for all of the naturally occurring isotopes. And when we have a weighted average, it means that we take into account the percentage of each isotope. So what is the naturally occurring percentage for each isotope? We can use chlorine as a very good example. It has two isotopes. It has chlorine 35, which makes up almost 76% of all chlorine atoms, and chlorine 37, which makes up the remainder. So we can do our atomic mass calculation here. We convert our percentage, that's here at 75.77. We turn that into a decimal at 0.7577. And then we have the mass of that particular isotope. We can take the percentage of the chlorine 37, turn it into a fraction, and then multiply it by the mass of chlorine 37. And when we work out that little bit of math, we get a value of 35.45 AMUs. And if you look at the periodic table, what you'll see is chlorine has an atomic mass of 35.45 AMUs. So that's an average mass of your sample that you would have for any sample of chlorine atoms. And here's one that you can try. The video for this particular problem is on YouTube, and you can find the link on Ilium, and you can go to a folder that says YouTube videos, and when you click on that, it'll take you to a folder in YouTube, and there's many different problems on there, and this is one of them. So one of the more important units that we use in chemistry is something called a mole. A mole is really the same thing as a dozen. It gives us a way of counting a very large number of items just with using smaller numbers. And so, for example, 12 donuts is equal to 1 dozen. In the same way, we have 6.022 times 10 to the 23 donuts. It's a whole lot of donuts. That would give us 1 mole of donuts. So the value for a mole is 6.022 times 10 to the 23rd, in the same way that 12 is always equal to a dozen. We can have a mole of anything, but because the number is so large, it only makes sense to have that large number of something for things very small. And if we look at how we calculated that value, it's equal to the number of carbon-12 atoms in exactly 12 grams of carbon-12. But here's a question we kind of want to ask ourselves, and we can have a little bit of fun with. How big is a mole, really? Well, if you had a mole of M&Ms, you could actually cover the United States to about a depth of 25 miles with a mole of M&Ms. If we had a mole of donuts, we could cover the entire Earth to a depth of about 8 kilometers, or about 5 miles. If we had a mole of basketballs, we could actually create a whole nother Earth with just a mole of basketballs. And this is my favorite. Who wants to be a millionaire? What if you were born with a mole of dollars? Well, if you had a mole of dollars, you could spend $1 billion every second of your life, and then 200,000 roughly of your kin could do the exact same thing. So that is a very, very large number. And yet, if we think about how big a mole of water might be. What if I had a mole of water molecules? That would only take up about 18 milliliters of space, of volume. And so molecules are very small, and a mole is very large. One of the more common calculations that we do is to convert between mass and moles. Now, when we write our reactions, we can actually write them in terms of atoms or molecules reacting. That doesn't do us much good because we don't actually add simple atoms or molecules into a beaker. We add much larger amounts. So we can actually think of these numbers in terms of moles as well. Because what ends up happening is that an element's mass of 1 mole of that material in grams is equal to that atom's mass of that element in AMUs. So we can get that from the periodic table. Okay, and once we get that information, it becomes a conversion factor. Now, a conversion factor is any time you have something per something else. The most common way of stating the mass of an element or of a molecule is in terms of grams per mole. But we can also invert that and get 1 mole per the same number of grams. Even though numerically they look different, symbolically they are exactly the same. It's just like saying that you have 12 eggs for every 1 dozen. You have 1 dozen for every 12 eggs. Even though one of those values is 12 over 1, and 1 is 1 over 12, numerically they look different. But what that means is that symbolically they are the same. Just some examples for you to try there on your own. So how do we use our molar mass? And let's say we want to find the number of moles of copper in a 35.8 gram copper sheet. Well, we want to write down what we have. So we have 35.8 grams of copper times, and if we look up copper on the periodic table, we see that we have 63.54 grams per 1 mole, or we can say that we have 1 mole per 63.54 grams. Now, we want this calculation to end up as moles, so we want to have moles on the top. We want our grams to cancel, so we want our grams on the bottom. So this is the conversion factor that we're going to want. So when we write 1 mole per 63.54 grams, you can see our grams cancel out. Let me change my color. Grams cancel and just leaves us with moles. Okay, and I'll leave the math to you so you can see how that comes out. What if we go the other direction? What if we want to find grams, but we're given the number of moles? Well, we can do the same type of calculation. We have 0.473 moles of titanium. Let me look up my titanium here. We have 47.88 grams per 1 mole, or 1 mole per 47.88 grams. Now in this example, we want our moles to cancel and we want to be left with grams. So we want to use that first conversion factor there. So we can go times 47.88 grams per 1 mole of titanium, and you can see that my moles of titanium will cancel and I can calculate a value there. There's lots of different ways of doing these calculations, so if you learned it in a different way, that's just fine. Now for molar mass, we express our molar mass of a particular compound in units grams per mole, just like we did for an element. And what we can do is just take the mass of all of the elements that are present in a compound and realize that if we just add up all of the molar masses of all of those elements, then we can get the total for a particular compound. So what we do is take the number of atoms of the first element times its atomic mass from the periodic table, plus number of atoms of the second element times its molar mass. And we just do that until we've calculated in all of the different elements that make up a compound. And once we do that, we end up with the molar mass of a compound. So as an example, we can do NH3, ammonia. We see that we have 1 mole of nitrogen there from our formula because there's only one nitrogen there. We look at the periodic table for nitrogen, and we have 14.077 grams per mole. We add that to the hydrogens, and we have 3 moles of hydrogen because of that 3 right there. And then the molar mass of hydrogen is 1.008 grams per mole. And when we add all that up, we get 17.031 grams, and that should be per mole. Okay, so that would be the molar mass of our ammonia. And here's an example for you to try on your own. This is also put up on YouTube, so you can take a look to see how it's done. For any of these problems that have a solution on YouTube, I do recommend that you try the problem on your own first, then go look at the solution. Now, anytime we're doing reactions, we need to make sure that we're balancing the reactions. Okay, so let's take a look at a reaction between H2 and I2. Okay, we're going to shrink ourselves down. We're just going to have a little bit of fun. We're going to shrink ourselves down to a molecular size and hop in our molecular sized aircraft. We're going to fly around this reaction. So what would we see? Well, we've got an H2 molecule, we've got an I2 molecule, and they are going to crash into each other. So when they do crash into each other, we've got a release of some energy, and what we see is that the hydrogen-hydrogen bond broke right there, and the iodine-iodine bond broke right there as well. And then we had a hydrogen-iodine bond form right there, and another hydrogen-iodine bond form right there. Okay, now we want to know, is it balanced? And when we say a reaction is balanced, it means that I have the same number of atoms of one element going in as coming out in the products. So I can't lose atoms, I can't gain atoms. I have to have the same number of atoms of each element in both the reactants and the products. So we can take a look at this reaction not only as a drawing, but also as a chemical reaction. And so we see that we have 2 hydrogen atoms here in the H2 molecule, and I've got 2 hydrogen atoms there in my products. I've got 2 iodine atoms from the I2, and I've got 2 iodine atoms in my products as well. So we are balanced, and mass has been conserved. I've kept all of my atoms from the reactants, and they show up in the products. Let's take a look at an unbalanced example to see how we might balance a problem. So here we have 2 hydrogen atoms in the reactants and 2 oxygen atoms in the reactants. In the products, I have 2 hydrogen atoms, and I've only got 1 oxygen atom, so that's not balanced. Okay, so we have to do something about that. We're not allowed to change the formulas of the reactants or the products, so we need to adjust how many of each species is present in order to balance. And what I mean by that is I can't just take my pencil here and put a 2 there and cause that to be H2O2. That would be bad. H2O2 is hydrogen peroxide. Very different compound. When you come in on a hot day, nothing better than a nice ice-cold glass of water. Really refreshes you. An ice-cold glass of hydrogen peroxide, yeah, that might kill you. So we really don't want to change the meaning of our reaction there. So let's go ahead and balance this reaction. So here we have our H2 and O2 going to H2O. We know that we need 2 oxygen atoms on the right. So to do that, we need to have 2 water molecules. So we're allowed to change the value here out in front of that molecule. So now when we check our balance, because now we have 2 oxygen atoms, so we should be balanced. Oh, unfortunately, by having that 2 in front of the water, we also changed the number of hydrogen atoms. So now I balanced my oxygen atoms, but my hydrogen atoms are now out of balance. But that's okay. That happens a lot when we're doing these. I can actually balance my hydrogen atoms by putting a 2 in front of my H2. And now I've got 4 hydrogen atoms on both sides and 2 oxygen atoms on both sides. Now when we balance a reaction like that, we generally use what's called a trial and error balancing method called balance by inspection. And all that means is you keep trying, making small adjustments as you go. If the numbers start to get too big, that probably means that you've made a mistake somewhere and you need to take another look at your numbers, maybe even start over. Well, here's a couple that we can try. We've got C6H14 plus O2 going to CO2 plus H2O. I just like to balance these going from left to right. And so actually I think this one is online as a video, so I'm not going to balance it here. And here's another one that I've got online. B2O3 plus NaOH goes to Na3BO3 plus H2O. So give both of those a try on your own, and then check the video to see if you get the coefficients correct. Now when we're doing reactions, a lot of time what we're worried about is how much material have we put in and how much material are we getting out of the reaction. We call that relationship stoichiometry. And stoichiometry is a term that relates amount of stuff in to the amount of stuff that comes out, our reactants versus our products. You can think of it just like you might in cooking. It's our values in a recipe. How much do I need to put into a particular recipe to get a particular amount out? So if we know how much material we're putting in, using stoichiometry, we can figure out how much product we're going to get out. So here's just a quick example initially of a filling for cream cheese or cheesecake. So if you take 5 eggs and 3 blocks of cream cheese and a cup of sugar, that should give you a filling for 1 cheesecake. If I wanted enough filling for 2 cheesecakes, I would just need to multiply everything by 2 in my reactants. I don't need to change my balanced reaction. I just need to know how to get those relations between them. Well, the same thing goes for a regular chemical reaction. Down below we have the chemical reaction for the formation of ammonia. So we have 3H2 plus N2 going to 2NH3. And there's lots of different conversion factors that we can make. Before we even look at those, we can see that we can do some of these conversions in our head. So if we had like 5 moles of N2, how much NH3 would we be able to make? And since for every 1 N2 that we put in, we get 2 NH3 out. If I put in 5 moles of N2, hopefully you can see that we should get 10 moles of NH3 out. You did that one in your head, and it's good to remember that because these calculations aren't particularly difficult, just need to keep straight which conversion factors you want to use. Here are 3 of the conversion factors of the 6 that we have for this particular reaction, and it gives the stoichiometric relationship between each of the products and reactants. Notice that the values in front of each particular reactant or product matches what we see for the balancing coefficient in the balanced reaction. I mentioned that these are 3 of the stoichiometric relationships. The other 3 relationships come from inverting each of these. And they become conversion factors, and you can always flip a conversion factor. Now when we're doing a reaction, a lot of times our reactants are not added in exact amounts. And there's a variety of reasons for that we're not going to get into. But if they're not in exact amounts, that means one of those is going to run out first and one is going to be present in excess. Usually what we want to find is which of those is going to run out first. And the reason we want to do that is because it's called a limiting reactant and it controls the amount of product. It limits the amount of product is a good way to think about it. Let's go back to that NH3 reaction that we just saw. Let's say we had 10 grams of H2, 10 grams of N2. How much ammonia could we produce? We can't just look at the amounts of H2 and N2 and say, well, we're going to get 20 grams. Reactions don't work that way. We need to check to see if we have a limiting reactant. Now, because we have an amount of 2 different reactants given, it's usually a good assumption that we have a limiting reactant problem, and we're going to have to figure out which of those is going to give out first. So the first thing we want to do is we want to convert both of our reactants to moles. So here we convert our H2 to moles, and we get 4.975 moles of H2. We get 10 grams of N2. We convert that to moles. We get 0.357 moles of N2. Now, we can't just look at the number of moles of each of those elements and say, well, the N2 is present in a lesser amount, so it's the limiting reactant. And the reason we can't say that is because the N2 and the H2 are used up at different amounts, or at different rates, because of the balancing coefficients. So we need to see which reactant is going to run out first by comparing the rates at which they're used. And we can use the stoichiometry for that. So for N2, it has a balancing coefficient of 1, so we can think of it as using 1 mole of N2 for every reaction that goes. So we divide the number of moles of N2 that we got here and put that here, and we end up with 0.3571 reactions. We can carry out the reaction 0.3571 times. It's okay that it's a decimal. Don't think too much about that. For our H2, we take our 4.975, we divide that by the 3. Okay, we use that 3 there because we have a 3 coefficient for the H2. When we divide that, we get 1.658. Because our nitrogen has a smaller number, it is my limiting reactant. This is the only thing that we use these values for, is to compare to each other and figure out which one is the limiting reactant. Okay, so now we're going to use the moles of N2 for the rest of our calculation, and we can ignore the H2. So using the N2, we have moles of N2. We can use the stoichiometric relationship between NH3 and N2 to calculate number of moles of NH3. And once we got the moles of NH3, we can use the molar mass to convert to grams of NH3. So when we do that, we get 12.1 grams of ammonia. Notice we don't get 20 out, even though we had 10 grams of each in. Okay, this is a fairly complicated problem, but notice that everything we did is nothing more than a series of conversion factors. And so it's very important to keep in mind as you go through here. You can do the conversion factors easily enough. You just need to know which one you're going to do. Unit analysis becomes very important here. If you can get from one unit to the final unit and do it with a proper unit analysis, chances are you've done the problem correctly. Now, in a perfect world, when we do a reaction like that, we get all the product that we would expect. This, however, rarely occurs. The example I like to use is with cookie dough. If you make a recipe with cookie dough, or if you buy tube cookie dough, it usually says you should get a certain amount of cookies out. However, we all know that we snack on the cookie dough as we're making the cookies, and we don't get as many cookies as we're supposed to. Now, I don't recommend snacking on the chemicals when you're working on a reaction. However, other things can happen that keep your chemical reaction from going all the way to completion. If we look at that previous problem with the ammonia, we saw that if we added 10 grams of N2, 10 grams of H2, we should get 12.1 grams of NH3. That 12.1 grams has a term, and it's called the theoretical yield. That's the amount of material we should get out. Well, let's say that we do the reaction, and we only got 7.8 grams of ammonia out. This is called the actual yield. Well, what happened? Well, we're not going to get into what could have happened, but something chemically happened that prevented us from getting all 12.1 grams out. That 7.8 grams, again, is called an actual yield, and it must be determined experimentally. You cannot calculate what an actual yield should be. And so to get the percent yield, we take the actual yield of what we got, divide that by the theoretical yield of what we expected to get, we multiply that by 100%, and we get 64.4%. That's not a bad value, it just is what it is. Some reactions are very low, below 10%. Some reactions are very high, above 90%. It just depends on the reaction and the conditions. And here's one for you to try a little bit later. The video for this particular problem is posted up on the YouTube set, and so try this one out and then check yourself to see if you get the right answer. Now in chemistry we do a lot with solutions. It's kind of what people think about when they think of chemistry usually, is solutions of different colors or whatever. But a lot of them have a very common similarity between them, and that's that most of those solutions have water as a solvent. When water is a solvent, we call those solutions aqueous solutions or aqueous solutions. We use water very frequently because it's a very good solvent. What makes it a good solvent is it is a very polar molecule, which means it reacts very well with ionic compounds. And these are our salts, and a lot of what we're dissolving are going to be salts. And so those two things interact very well and makes dissolving a lot of those salts energetically favorable. Now, when we're making solutions, we don't just want to throw in any old amount of our solute in there. So we need some way of expressing how much solute is actually present in a solution. How much material do we have dissolved in there? Well, we use the term molarity by far most often. So it's a very common way of expressing concentration. And molarity is actually the moles of solute divided by the liters of solution. Notice that this is liters of solution and not liters of solvent. Okay, so liters of solution includes both the solvent and the solute present in that solution. So, as an example, if you went down to a storeroom or a stockroom and you saw that we had 0.37 molar, it's how we say molarity with a capital M, molar, nitric acid solution, it means that for every liter of that solution, we should have 0.37 moles of HNO3 present in that liter. Now, when we have molarity, notice that we do have 2 units there. We have moles of solute per liters of solution. And anytime we have something per something else, it can be a conversion factor between those two units. So molarity becomes a conversion factor between moles and volume. It also means that we have a lot of relationships set up between molarity, volume, and the number of moles. And we're going to use that here in just a little bit. So here's just an example for you to take a look at. Let's say I take 0.38 grams of sodium nitrate. I dissolve that in some water to make 50 milliliters of solution. We want to know what would the solution's concentration be in moles per liter or molarity. Well, I don't have the units that I need for molarity, but we do know how to get that. We're given grams of sodium nitrate. We can convert that into moles of our solute. We have 50 milliliters of solution. Notice that our molarity needs liters of solution, so we just need to convert that to liters. And I'll put here we need to convert that into moles. And so once we've got the moles of our solute and the liters of our solution, we can divide those properly and find the molarity. So we mentioned that molarity can be used as a conversion factor. We can use it to find how much solute we need for a particular concentration. We can figure out how much is in a particular volume of a known molarity solution. Okay, so we mentioned it can be used to convert between volume and moles. Once we find volume in moles, we can then move that to a moles to grams conversion. Let's take a look at an example here. So how many milliliters of a 1.5 molar sodium chloride solution are needed to get 100 grams of sodium chloride? We know how many grams we want. We want 100 grams. But in order to get grams, we first need to find moles, because moles are a unit in that 1.5 molar NaCl. Grams are not a unit. Once I find the moles, I can use the molarity and the moles and use that relationship to find the volume. Once I find the volume, I can convert that volume into proper units if any further conversion needs to be done. Let's look at that one as an example. So here we're going to turn our grams of sodium chloride into moles of sodium chloride. I've got 58.44 grams per mole. That's just the molar mass of sodium chloride. I get that by adding sodium and chlorine together on the periodic table. So I have 1.7111 moles sodium chloride. I want to turn that into a volume. So in order to get 1.711 moles of sodium chloride, I see that I need 1 liter of solution to get 1.5 liters of sodium chloride. Okay, and that comes from the concentration of the solution. So it turns out I need a little bit more than 1 liter. If 1 liter gives me 1.5, then to get 1.7, I need a little bit more than that, and that's exactly what my calculation shows. If I wanted that in milliliters, which is a common unit that we measure in, we just convert our liters to milliliters and we get 1,141. Now, sometimes when we're going to make a solution, many of the chemicals that we want to make into a solution or use as a solution in the lab need to be made more dilute than what we buy. Many of the materials we buy, especially some of our stronger acids, get bought in a very concentrated form, and the form that we want to use them in needs to be more dilute. So what we want to do is calculate how much of that concentrated solution we need so that when we dilute it to the volume we want, we'll have the final concentration we want. Well, we can manipulate our molarity equation. We see that we have our molarity is equal to moles over volume in liters. If I move that volume over here, multiply both sides by volume, I now have volume times molarity is equal to moles. So if we think of our solution, we're going to take a certain volume out of a concentrated solution and put that into a beaker. And then I'm just going to add water to that beaker to dilute it. I haven't changed the number of moles of that material because all I've done is added water to it. I have to change the concentration of it, but I haven't changed the number of moles. So what that means is that the initial number of moles of the material that I'm trying to dilute is going to be equal to the final number of moles that I'm diluting. The only difference is the volume of the solution that they reside in. So, in order to get our moles, we can calculate moles just like we did here as volume times molarity. So the volume times the molarity of my initial solution is equal to the volume times the molarity of my final solution. So a lot of times we say it as MI-VI equals MF-VF, or we can also say M1-V1 is equal to M2-V2. Very easy equation to use and very handy in the lab.
So let's talk about what equilibrium is and how we study it, how we understand it, and ways that we can actually manipulate it. So if you go back and look at a lot of the reactions that you've done up to this point in both semesters that you've had of chemistry so far, you'll notice that a lot of times we draw our arrow for our reaction in a single direction. Well, as it turns out, very few reactions only go in one single direction, and we saw a little bit of that here in this last lecture in kinetics. What we can also see is collisions between product molecules that can recreate reactants, and so products re-react and form reactants all over again. So as a reaction moves in the forward direction, well, what happens to that? So if we start with just reactants and move a reaction in the forward direction, what we get is those reactants reacting, forming products, and as a result we have fewer reactant molecules present, and so as we've seen, that forward reaction rate slows down. But as that forward reaction rate slows down, because of fewer reactant molecules, what we're making is product molecules, and so we're increasing the number of product molecules, and as a result the reverse reaction rate begins to increase. So we have the forward rate decreasing and the reverse reaction rate increasing. At some point during that reaction, the forward rate and the reverse rate will be equal, and the reaction will have reached a state of what's called dynamic equilibrium. Now at that point, the concentrations have stopped changing, but that doesn't mean that the reaction is stopped. The molecules have not stopped moving around, they have not stopped reacting. It just means that the concentrations have stopped changing. Now, when we see this, the term equilibrium, one of the common misconceptions people think is that the concentrations of products and reactants are equal, and that just isn't true. The equilibrium is referring to the reaction rates, and the reaction rates are equal both in the forward and the reverse direction. So when we write that a system is in an equilibrium state, we indicate that with a forward and reverse arrow, as we see here with A and C. And so forward and reverse arrow. If you want to see how equilibrium is expressed mathematically, we can do that using what we've learned from our kinetics chapter. We know that for equilibrium to be reached, we have to have the forward rate equal to the reverse rate. So we say rate forward is equal to rate reverse. Well, we learned how to express the rate in terms of the rate constant and concentration, and here we're going to use our just an example reaction of A turning into C, that reaction in equilibrium. So the forward rate can be expressed as the forward rate constant, K forward, times concentration of A, and the reverse rate constant, or it's going to be equal to the reverse rate, which is equal to the reverse rate constant, K reverse, times concentration of C. Well, let's rearrange that and put all of our rate constants on one side and our concentrations on the other. So we have K forward over K reverse is equal to concentration of C over the concentration of A. Now we see that we've got two rate constants there, K forward and K reverse, and so K divided by AK is going to lead to another K. One constant divided by another constant gives you yet another constant. So that value is in fact a constant. And those concentrations for C and A are going to be equilibrium concentrations. These are not initial concentrations where the reaction started. These are going to be equilibrium concentrations where the reaction has finished up when it reaches equilibrium. Well, we're going to call that ratio of the forward rate to the reverse rate K equilibrium. And notice that it's a capital K, and we have a little EQ down there to indicate equilibrium. As the semester goes on, we'll have several different equilibrium constants, but they all follow the same basic premise. We're going to have products over reactants. Okay, so here we have C over A. It was A turning into C. So it's a concentration of products over concentrations of reactants. It'll get a little more complicated than that, but not by much. Let's look at a little bit more complicated reaction here. It's still generic. So we have A plus B going to C plus D. And our small a's, b's, c's, and d's, those are just our stoichiometric coefficients from the balanced reaction. So for a balanced reaction, we can write our equilibrium constant expression directly, which is very much different from what we learned in kinetics. So, but for equilibrium, we can do this. So the equilibrium constant, KEQ, is equal to products over reactants. And so we have the concentration of component C raised to the power of its stoichiometric coefficient from the balanced reaction, so little c. And then we have times concentration of D raised to little d. So it's my products over my reactants. So we have concentration of A raised to little a times concentration of B raised to little b. Let's look at it for an actual chemical reaction here. We've got N2O4 in equilibrium, two NO2s. So products over reactants. So we have KEQ is equal to concentration of NO2 squared over concentration of N2O4. It's just that easy. Now the equilibrium concentrations are very important. They can vary within a single reaction depending on what starting concentrations were, but the most important thing about equilibrium is that that ratio must always hold true. And so here's a table for the reaction H2 plus I2 goes to 2HI. And we have our equilibrium constant expression there. It's going to be concentration of HI squared over concentration of H2 times concentration of I2. Now notice here we have several different types of initial concentration situations and different equilibrium concentrations as well. So in this first reaction, both H2 and I2 started at half molar. They finished at certain equilibrium concentrations, and what we find is that the ratio of those, when plugged into the equilibrium expression, we have equilibrium constant of 50. Now, in the next one, we started with no H2, no I2, and half a mole or half molar HI. We find a very different set of concentrations at equilibrium for the H2, I2, and HI, and yet we still end up with an equilibrium constant of 50. On the third example, we have half molar concentrations of all species, and we have different values for the equilibrium concentrations again, but once again, those concentrations plugged into the equilibrium constant expression gives us a ratio of 50. So this value must be met, and that gives us a lot of power when we're looking at equilibrium constant expressions, the equilibrium constants, and what we can relate to them. And we'll see this as we move along, how it can help us. What does the value of that equilibrium constant tell us? Well, we can have it tell us where that equilibrium lies. What can I expect to find inside my reaction vessel once that reaction reaches equilibrium? So if the equilibrium constant K is much larger than 1, and here's an example of ozone turning into oxygen, it's got an equilibrium constant of 2.54 times 10 to the 12th, that's a lot larger than 1. What we're going to find in the reaction vessel at equilibrium is a lot more product than reactant. So for this type of reaction, we would say that the reaction favors the products. If K is much smaller than 1, so here's an example where we have a chlorine molecule breaking apart into 2 chlorine atoms, has an equilibrium constant of 1.4 times 10 to the minus 38. Very, very tiny number. What this means is the reaction really doesn't like to happen, and you have very little product form. So for this reaction, we would say that it favors the reactants. If a K is in the vicinity of 1, then what you're going to have left is a mixture of reactants and products present, and neither products nor reactants are favored in this case. And again, at equilibrium, you're going to have a mixture of both reactants and products, and you're going to have substantial amounts of both of those. Now there are some special cases when we're writing equilibrium constants, and we've talked about these just a little bit. I'll reiterate them here. So anytime we have a reaction that involves pure liquids, especially water, it seems to show up a lot in these reactions, or if we have a pure solid indicated by an S in our reaction, we leave those out of our equilibrium constant expressions. Now the reason for this is that these two phases compress very little with a change in pressure or even with a change in temperature. So the concentration of a pure liquid or a pure solid is generally based on the material's density. That determines the number of moles in a certain volume of a substance, and so because that's a constant value, we work that constant into the equilibrium constant already, and we don't have to worry about it. So when we are writing our equilibrium constant expression, we leave out any liquids and any solids. Let's take a look at some examples of that. So here we've got acetic acid and water dissociating into the acetate ion and hydronium ion. And when we write the equilibrium constant expression, we just have products over reactants. But notice that we have left out the value for the concentration of water. Concentration of water is a constant. It's somewhere in the range of 55. And so that's already worked into the value for Kc. And so we can leave it out of the equilibrium constant expression. Let's look at another one here. So the decomposition of calcium carbonate solid, it decomposes into calcium oxide solid and carbon dioxide gas. And again, when we write the Kc here, it's just the concentration of CO2. We've left out the calcium carbonate and the calcium oxide because those are solids. That means their concentrations don't change and their values are already worked into the value for Kc. An important concept in equilibrium chemistry is this idea of a reaction quotient, and we just call that QC. You could call it QP if we're calculating for gases. It's very similar to the Kc. The only difference is that when we're calculating an equilibrium constant value, Kc, we're assuming that the concentrations we're using are equilibrium concentrations. When we're doing a Qc, we don't make that assumption. So we just use the concentrations at hand, and then we can use that value to determine if the reaction is at equilibrium, or if it has to shift more to the right to get to equilibrium or to the left to get to equilibrium. So we can use the value of Kc to determine which direction that reaction has to move to reach equilibrium. Well, let's look at a reaction here, H2 plus I2 going to 2HI. We would write an equilibrium constant expression here as Kc is equal to Hi squared over H2 times I2. And again, because this is an equilibrium constant expression, we are assuming that those concentrations there are equilibrium concentrations. We write our Qc expression in the exact same way. The only difference is the concentrations there don't have to be equilibrium concentrations. They can be any concentrations at any time t. And then we're going to compare the value that we get for Qc with the value we get for Kc. So let's take a look and see how we do that. So if we calculate a value for Qc and it's greater than Kc, that indicates that the products in the numerator are more abundant than they should be at equilibrium. And that means that the reaction needs to move towards the reactants, or it needs to move to the left in order to reach equilibrium. Vice versa, if Qc is less than Qc, that means the reactants are more abundant than they will be at equilibrium, or you can think of it as we don't have enough product than we should to reach equilibrium. And so that means that the reaction is still moving in the forward direction in order to reach equilibrium. So we would say that that reaction is shifting right. And if we find that our value for Qc is equal to Kc, well, that means that our concentrations are in fact equilibrium concentrations and the reaction is at equilibrium. Let's look at an example using our H2, I2, and Hi system there. So we have a Kc value for this reaction at 54.3. It's something that we would look up. And so we have this reaction taking place. We took a sample from this reaction and analyzed it, and we found the following concentrations. So what we want to know is the reaction at equilibrium? And if it's not at equilibrium, which way does it need to shift to reach equilibrium? Or you could say, which way does it still need to proceed to get to equilibrium? Well, let's find a value for Qc. We know the value for Kc. So we see we have Hi squared over H2 times I2. Plug in our values that we found, and we find a Qc of 111. Now, a value of 111 is greater than the equilibrium constant, so this reaction has too many products, and as a result, we have to, the reaction is going to be moving to the left. So you're going to have more collisions of product reforming reactant here in order to reach equilibrium. And what Le Chatelier's principle covers is a general rule looking at how a reaction will respond in order to restore equilibrium after a disturbance throws a reaction out of equilibrium. So let's take a look at some of the different ways that we can disturb an equilibrium. We can change the concentration of a component. So if we can imagine a reaction that's at equilibrium, and perhaps we add something more to the reaction, or maybe we take something away, how will that reaction respond? If we have a reaction that takes place in the gas phase, either a pressure or volume change can certainly impact where the equilibrium lies for that particular reaction. Or we can certainly change the temperature of a reaction, and when we change the temperature, it affects a lot of different things, and one of the things it might affect is the position of equilibrium for a reaction as well. So if we state Le Chatelier's principle in a very simple manner, we just say that if an external stress is applied to a system that's at equilibrium, the system will adjust or shift to partially offset that stress and restore equilibrium. Let's take a look at concentration changes first. So let's consider this reaction at equilibrium. So we've got iron thiocyanate, which is a red color, iron 3 plus yellow, and the thiocyanate ion colorless. So that reaction there is in equilibrium. It's got a Kc as we see there, iron 3 plus times SCN minus over the iron thiocyanate complex. Now let's say that we've got this mixture at equilibrium and we add some sodium thiocyanate. Now sodium thiocyanate is a salt. It's going to be a soluble salt since it's a sodium salt and will readily dissolve in water. And when it dissolves in water, we add, in essence, some thiocyanate ion there. And what we find is that this concentration turns more red than it was before. Well, why was that? Well, we've increased the thiocyanate ion. The solution was at equilibrium. We've now increased the thiocyanate ion concentration, and in doing so, we've taken that reaction out of equilibrium. So we've disturbed the equilibrium. At this point, the reaction has too many products. The thiocyanate has increased the amount of products. So this means that the rate of the reverse reaction has increased, and that means that the reaction will shift back to the left or towards the reactants in order to restore that equilibrium. So in shifting to the reactants, we're shifting towards that red complex and the solution turns more red. Let's take a look at another example here. So the reaction of iron 3 oxide with carbon monoxide is used to reduce iron ore to iron metal. So this is one of the ways that we get iron metal from our metal plants. So we've got iron oxide there, iron 3 oxide, reacting with 3 carbon monoxide gas, and we get iron liquid and CO2 gas. So what we want to do is use the Chtelet's principle to predict the direction of the reaction following these disturbances. So let's say that we remove carbon dioxide. And I've got these little graphics on here. Hopefully they'll help with the visual here. So we're going to remove CO2. So we are removing a product. Now in our little graphic there, we can imagine the removal of something as a down arrow on that side, and it's going to tip our teeter-totter, and what we want to see is what ways are the balls going to shift. So we shift that down and the balls move to the right, and that indicates that our reaction will shift to the right. By removing a product, the reaction is going to shift in a direction to replace that product, and that means shifting to the products to replace the CO2 that we've removed. What if we remove carbon monoxide, something in the reactants? Well, in the reactants, so we're removing something, so again we're going to use a down arrow, only this time, since we're removing a reactant, we're going to put that down arrow on the left-hand side. And we see when we move that down, the balls shift towards the left-hand side. So again, when we remove something, the reaction wants to shift in a direction that will replace it. So by removing a reactant, we're going to have a slower forward reaction, and the reverse reaction is going to be faster now, and it's going to try to replace what was removed from that reaction. So here the reaction would shift to the left or shift towards the reactants. Now this one's a little bit tricky, adding iron oxide. And you'll notice that I don't have my little teeter-totter there. Well, if we look at the state of iron oxide there, we see that it's a solid. Now remember, solids are not included in the equilibrium constant expression, and if they're not part of the equilibrium constant expression, then adding or removing those components is not going to affect the position of equilibrium. So it also does not apply when we apply Le Chatelet's principle to the removal or addition of the Fe2O3. The same would also be true as if we removed iron liquid. It just doesn't affect the position of equilibrium because it's not part of the equilibrium constant expression. Well, now we can take a look at how Le Chatelet's principle applies to pressure and volume changes to materials in the gas phase. Now when a pressure change occurs, anything that's in a condensed phase, in other words liquids or solids, are not normally affected because they don't generally compress. They're in a compressed form already. So as a result, their number of moles over volume remains the same, which means that their concentrations remain the same. Gases, however, do compress, and when we compress a gas, the number of moles does not change, but the volume does change. And so by changing that volume and not changing the number of moles, we're actually changing the concentration. We would be increasing the concentration as we compress a gas. So the concentration is going to change most for the species with the largest number of moles. What this means is that when we take a look at how pressure and volume changes are going to affect a reaction, is that when that pressure is altered by a change in volume, there's going to be a greater effect on concentration for the side, either products or reactants, with the greatest number of moles in the gas phase. The reaction will shift to the side with the fewer number of moles of gas when pressure is increased, and vice versa. If we are increasing the pressure by lowering the volume, that increases the pressure on the system. The Chtelet Principle says that the system wants to offset that increase, and so the system is going to shift in order to decrease the pressure that was added. In doing so, it shifts to the side with the fewest number of moles of gas. So here we have PBS solid plus 3O2 gas goes to PBO solid plus 2SO2 gas. What happens when the pressure is increased? Well, when they increase the pressure there, the reaction is going to want to shift in a way that reduces the pressure. So it's going to shift to the side that has fewer moles of gas. In this case, it's going to shift to the product side because we have 3 moles of gas in the reactant and only 2 moles of gas in the product. So by going to the side with 2 moles of gas, the pressure will be decreased and the change in the alteration of equilibrium, or the disturbance in equilibrium, will be offset. Now what if we decrease the pressure? Well, if we decrease the pressure, then the reaction is going to want to respond to offset that decrease, and it's going to want to increase the pressure. So it's going to shift to the side that has more moles of gas because that will increase the pressure. So if we decrease the pressure, the reaction will shift to the left towards the O2 since there's more moles of gas in the reactant side. What if we mess with volume? What if we increase the volume? Well, if we increase the volume, that's going to decrease the pressure. Decreasing the pressure, we saw, causes a shift back towards the reactants. If we decrease the volume, that's going to have the effect of increasing the pressure, and the reaction is going to want to shift in the direction that lowers the pressure, so that's going to shift back towards the products. Here's another reaction here where we have only one gas there, Cl2, and we would see if we increased the pressure, then the reaction will want to shift to the side with the fewest number of moles of gas. So that would be the reactant side. So if we increase the pressure here, it would shift to the left. If we decrease the pressure, it's going to want to shift to the side with more moles of gas, and it's going to shift back towards the products. Let's look at another example here, or some more examples. We want to know how each of these reactions responds to an increase in pressure caused by a decrease in volume. So we have N2O4 going to 2NO2. So an increase in pressure. So the reaction is going to want to shift to the side with the fewer number of moles of gas, because fewer number of moles of gas is going to lower the pressure. And so we see that on the reactant side, we have N2O4, 1 mole of gas. And in the product side, we have 2NO2, so that's 2 moles of gas. So this reaction is going to shift to the left towards the reactants. Here we have 2CO gas going to carbon solid and CO2 gas. So again, if we increase that pressure, the reaction is going to want to shift in a way that offsets that increase. So it's going to move to the side with the fewer number of moles of gas. Well, we have 2 moles of gas in the reactants, and we only have 1 mole of gas in the products. So this reaction will shift towards the product side to offset an increase in pressure. In this one here, we have carbon monoxide plus H2O goes to CO2 plus H2. In both sides, we see that we have 2 moles of gas. So an increase in pressure will have no effect on the equilibrium here, because whichever way the direction would shift would cause 2 moles of gas to exist. So the reaction here has no way to offset an increase in that pressure, and the equilibrium would be unaffected.